Faculty of Engineering, University of Nigeria, Nsukka, 2020 Sustainable Engineering and Industrial Technology Conference, presenting on the topic effect of alkali and sodium sulphite treatment of various concentration, soaking time, and temperature on the tensile strength properties of banana fiber reinforced epoxy composite. The authors are Chukwuemeka, Sylvester, Ezema, Stanley, Chibeoso, Udochukwu, and Emmanuella. Introduction. Composite material, as we all know, is a combined assembly of two or more constituent materials, giving a synergizing effect in the resulting material. In a composite material, the two main constituents are the reinforcement and the matrix. The reinforcement gives the composite its rigidity and strength, and the matrix gives it the flexibility. So one of the materials we used as reinforcement materials are natural fibers. Because of the depletion of the oil reserves, many researchers are beginning to pick interest in natural fibers because they are lightweight and they are eco-friendly. So one of the natural fibers we use is banana fiber, which is a very eco-friendly material. And the polymers we use are epoxy resin, polyester resin, and vinyl ester resins. So background of the study. Banana fiber is a rhizomatous plant and is commonly grown in 120 countries around the world, including Nigeria. It's available all year round and is eco-friendly and can also be recycled, and it's also a low-cost material. So it has been established that chemical treatment increases the mechanical properties of natural fiber. Now, sodium hydroxide causes more lattice transformation more than other alkalis such as potassium hydroxide, lithium hydroxide, calcium hydroxide, etc. Now, in the separate research done by Ezema et al., we found that addition of sodium sulphite to this sodium hydroxide had more improvement in the mechanical properties of the banana stem fiber after treatment. Tensile and Hashim have investigated that treatment time, temperature, and concentration are the main variables which affects interfacial strength of our natural fibers. That lignocellulose and hydrophilic nature of banana fiber stem fibers is what hinders them from being used as a reinforcement material in composite, because they absorb moisture and there is no interfacial bonding between the fiber and the matrix. So Ezema et al. Have used sodium hydroxide and sodium sulphite mixture in the treatment of banana stem fiber, which shows an improvement in the mechanical properties of the fiber by 8.1%. The problem is that the effect of concentration, temperature, and soaking time of the NaOH and sodium sulphide mixture were not ascertained. So we find that there is a need to study the effect of these parameters in NaOH and Na2SO4 mixture on the tensile properties of the banana stem in a reinforced epoxy composite in order to determine the optimum treatment concentration, time, and temperature of the chemicals. Aim and objective. The main aim of this subject is to investigate the effect of sodium hydroxide and sodium sulphite mixture of various concentration, soaking times, and temperatures on the tensile strength properties of banana stem fiber in a reinforced epoxy composite. The objectives are to study the effect of NaOH plus Na2SO of various concentration, soaking time, and temperature on the tensile strength properties of banana stem fiber, to determine the optimum treatment parameters of the fiber that will yield the best tensile strength of the composite. And the third one is to produce banana fiber composite in order to explore its potential usage. Fourth one is to develop regression models that will predict the effect of soaking time, temperature, and concentration on the tensile strength properties of banana fiber in a reinforced epoxy composite. Significance and scope of this study. The significance is that banana fiber are hydrophilic in nature and needed to be treated. This will help to ensure the compatibility between the fiber and the matrix. And now, since concentration of chemical, soaking time, temperature are the major determining factors in fiber surface treatment, there is need to study the effects in order to determine the optimal soaking time, concentration, and temperature of the two mixture of the chemicals that will give us the best treatment parameter in the reinforced epoxy composite. The focus of this study is limited to banana stem fiber surface treatment. This was done using Taguchi-based design to vary the treatment parameters v soaking time, temperature, and concentration of the alkali and sodium sulphite mixture in order to ascertain their significance on the fiber and then optimize the tensile strength properties in the reinforced epoxy composite. That's our scope for this study. So literature review. In our literature review, we saw that Ezema et al. Treated with sodium hydroxide and sodium sulphide for 2 hours with a concentration of 4% for sodium hydroxide and 2% for sodium sulphide. And these are the maximum they got, which is 4.0 megapascal at 4% and 2% of the reagents. So Venkateshwaran also they did the same thing, but here he treated with only sodium hydroxide, and at 1 hour he got 33.6 megapascal at 1% of the sodium hydroxide. Being Battery et al. Did the same thing with 5% and treated for 24 hours with uses epoxy for this and compression molding in fabrication. Alavi et al. Did the same thing, that is concentration of 5%, 10%, and 15%. Then Malin et al. Studied with sodium hydroxide, treated at 5% for 1 hour. Jom et al., these are the parameters he used. So justification for the study. So far, to the best of our knowledge, it is justifiable to research on this work since presently none of the research works are focused on varying the soaking time, temperature, and concentration of the NaOH plus Na2 mixture to determine the optimal values that will give the best tensile strength of the composite. Methodology. The materials we use for this research are banana stem fiber, epoxy resin with Epoxy 105 part A and part B. Part B is the hardener. Sodium hydroxide with those product codes, sodium sulphite with the product code. So the fiber treatment, surface treatment. So how we selected our parameters is based on literature we conducted, the consideration chosen by other researchers in banana fiber surface treatments, which gave the highest mechanical properties when sodium hydroxide and sodium sulphite were used, ranges from 1% to 10%. And consequently, the soaking time ranged from 1 hour to 5 hours. Temperature ranged from room temperature to 7 degrees Celsius. So this helped us to determine the range of parameters which we chose. So below in figure, table 1, is the chosen parameters, the parameters we chose for this research. You see that we have a selected parameter. So we have soaking time of 1 hour, 2 hours, 3 hours, 4 hours, and then 5 hours. And concentration, we have 2%, 4%, 6%, 8%, and 10%. So that means for sodium hydroxide we chose 2%, sodium sulphide we chose 2%. So room temperature started for the temperature started from room temperature to 70 degrees C. So methodology. So we use the Taguchi based designs for this our experiment. So the Taguchi analysis was Kennedy Taguchi was an engineer and a statistician who developed the Taguchi method by introducing the loss function and experiments extending with an outer array. So the 3 equations that Taguchi generated for quality loss function: larger is better, smaller is better, and nominal is best. Because we are looking for increased optimal value, so that's why we're using larger is better signal to noise ratio in our analysis. So this table 2 shows the Taguchi generated Taguchi design. So we see that each of the parameters there is 5. So we have 25 experimental runs in our Taguchi design. So our experimental setup is shown in figure 1. So what we have here is that we have a beaker, then we insert our banana fiber inside the beaker, which will now dip into a water bath and then cover it. It's left open in the diagram just for emphasis. Then we now put the regulator at that particular temperature to regulate the temperature at which we are treating. So figure 2 is the treated sample, while figure 3 is the untreated sample. So composite fabrication, we fabricate our composite based on HTM standard, and hand layup technique was used to laminate the composite. So equation 1 shows the formula we use in calculate our volume fraction. We used analysis of variance to analyze our data, and Lagrange regression model were generated based on equation 7. Then ANOVA, which was done, is used, there's the equation 6. So if the observed value is greater than the critical value, we reject the null hypothesis. But if it's less than the observed value, we accept the null hypothesis. And it was done on 95% significance level of the data. So quadratic regression model was also generated. So the precursor quadratic equation in equation 8 was adopted, and equation 9 is the metric form of equation 8. So this is generated experimental matrix and response value for tensile strength, and is shown in table 5. So below we have untreated, which gave us 62.27. The table 4 shows the response table which we generated from Taguchi's design, and it's shown graphically that soaking 1 hour gave us the highest mechanical property, and 8% concentration, then temperature of 40 degrees, all give us the highest parameters, which give us the highest tensile strength property of the fiber. So we now going back to the lab to compare our regression, the experimental optimal values which Taguchi based design gave us to the untreated. So we did a confirmation experiment based on those parameters, and we saw that there is 72.86 megapascal of strength. When we now compare it with the original, the untreated, and we found out that there is 17.01% increase in the tensile strength. Hence, there is improvement in the tensile strength of the banana stem fiber after treatment. So, table 5 also shows us that the model, that the regression analysis results in tensile strength shows that all the parameters were significant, with concentration the most significant, with a contribution of 49.12%, followed by the soaking time and then temperature. The regression model that was generated, which is the linear regression model, while equation 15 is the quadratic regression model. So which shows us, you see the R-square value, which shows that the contribution of these parameters is 72.52%. That shows the variation, which shows how the parameters are being contributed to the mechanical and tensile properties of the fiber. So the graphs we have in figure 9 and figure 10 shows us the comparison experimental results with the predicted linear regression model to the tensile strength. So we see that when we now see that the comparison between the two shows that the model we generated for the quadratic regression model is predicting better with a Poisson correlation coefficient of 0.87 more than the linear regression model. Concluded that the optimum condition for the tensile strength of the banana stem fiber require composite consider are soaking time of 1 hour, concentration of 8%, and temperature of 40 degrees. The tensile strength and equal analysis shows that there is completion of 21.9% for soaking time, and the concentration 49.12%, and then the temperature 16.6%. The developed quadratic regression was a better predictor, and the confirmation test shows that there is 17.01% increase in the tensile strength of the banana fiber after treatment. So recommendation, we recommend that another method of optimization should be used other than Taguchi in order to validate the predictions made by Taguchi in this work. So more independent variables which affect the mechanical properties of the fiber, such as weight, fiber volume, fiber direction, etc., should be added to it. So these are the references we made in the course of this work. Thank you for your audience. Thanks. Bye.